Hello everyone, welcome back to our NDT training session. I am Mutalakshmi Kanagaraj, ASNT Level 3 in 10 methods, API, PMP and Frozio Level 3 certification holder. And it's great to continue our journey into the world of non-destructive testing. Today we are going to dive deep into the fascinating world of ferromagnetic material characteristics, a fundamental concept for anyone working with magnetic testing method. This is crucial knowledge for anyone involved in non-destructive testing, particularly when dealing with magnetic methods. Let's break down the key concept presented in our material. Magnetic flux and flux density. Magnetic flux. This refers to the total magnetic field lines in a given area. Think of it as the total amount of magnetism passing through the surface. This is the magnetic flux. Flux density means this is more precise measurement defined as the magnetic flux per unit area. It tells us how concentrated those magnetic field lines are. Regarding units, we used Maxwell for flux and Gauss for flux density. This is for flux and this is for flux density. However, in the current SI system, we use Weber and Tesla. Let's move the next slide. Magnetic hysteresis. This is a fundamental concept for understanding how ferromagnetic materials behave when exposed to magnetic field. The hysteresis curve illustrates the relationship between magnetic field intensity and flux density. It shows us how a material's magnetism changes as the applied magnetic field is varied. Let's move to the picture and we will compare to the key characteristics. First, initial magnetization, virgin curve 0 to P1. This is the 0 point, this is a P1, this is a virgin curve, showing how the material first magnetizes as the magnetic field intensity applied. This 0 is the point of 0 flux density and 0 magnetic strength. This P1 is the highest point of the magnetic field. The material flux density, the material how the first magnetized, and the P1 is the saturation point. At this point the the flux density, this is the flux density, B is the flux density, reaches its maximum, meaning no further increase in B occurs. Even if you keep increasing the magnetic flux density at the saturation, at all magnetic domains within the material are aligned. So when the applied magnetic field intensity is reduced to 0, the material still have some magnetism. So it can't reach again 0. This BR is a residual magnetism when H is equal to 0. The residual magnetism is called remanence. At remanence, some magnetic domains remain aligned while others become random. Next, the cohesive force, Hc. In between the 0 to BR is called a residual magnetism. So Hc is a cohesive force to bring the flux density back to 0 after the applied field is removed. A reverse magnetic field intensity H must be applied. This is a magnetic field intensity, and here we reverse the magnetic field intensity must be applied. This required reverse hedge is known as the coercive force. So this point is this is the coercive force. At the coercive force, the domains rotate 90 degree or 180 degree, effectively reversing their polarity. If the reverse hedge is further increased, the material will eventually reach maximum negative flux density. So here is the negative flux density. This loop formed by cycling the magnetic field intensity through positive and negative values, illustrating the material's magnetic memory. To demagnetize a material, you essentially perform repeated this hysteresis cycles to reduce the alignment of its magnetic domains. This is the how we demagnetize the material after removing the external magnetic field. The shape and size of the loop tell us a lot about the material's magnetic property. It reduces its size and then finally it gets zero for fully demagnetized. So let's move the next slide. Magnetic domains behavior and magnetic permeability. The behavior of magnetic domains directly explains the hysteresis loop. At saturation point, all magnetic domains within a material are aligned with the applied magnetic field. At reminiscence, when the external field is removed, some domains remain aligned, while others become random, resulting in the residual magnetism. At coercive force, to reduce the flux density to zero, the domains must rotate 90 degree or 180 degree, effectively reversing their polarity. Demagnetization. Achieving full demagnetization often involves repeated hysteresis cycles which gradually reduce the overall domain alignment. Next, let's talk about the magnetic permeability. This is a measure of the ease with which a material can be magnetized. It's calculated by the formula mu is equal to B by H. Flux density divided by magnetic field intensity. B is a flux density and H is a magnetic field intensity. Materials with high permeability are easy to magnetization. A good example is annealed low carbon steel. Conversely, materials with low permeability are difficult to magnetization. Hardened steel is a prime example. Reluctance and material influence. Finally, let's consider the opposite of permeability and how material properties affect magnetism. Think of reluctance as the resistance of magnetic field change. It's analogous to electrical resistance in the circuit. It has an inverse relationship with permeability. A material that is easy to magnetize will have low reluctance and vice versa, because it's an inverse process. If high permeability means reluctance is low. And the magnetic properties of a material are not static. They are significantly affected by several factors. like temperature, chemical composition, grain size, microstructure. These factors lead to distinct hysteresis loop behaviors for different materials. In hardened steel, the material typically exhibits low permeability. It's harder to magnetize. It also has high retentivity and a high cohesive force, making it difficult to demagnetize once magnetized. Annealed steel, it contrasts. Annealed steel shows high permeability, meaning it's easy to magnetize. So, high permeability means low reluctance. So, it's easy to magnetize. It has low retentivity. That means retentivity means residual magnetism is very low and is easy to demagnetize. I hope this concept is now clear to everyone. I will prepare some questions for this session. Comment your answers in the comment box. If you have any further clarification, comment on comment box. Thank you.